SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture number 3 in the course Introduction to Robotics. Today we'll be talking about spatial descriptions and transformations. In the last class we looked at the various joints that are used to make up robotic systems, and then different kind of robots that can be made by using different kind of joints and their corresponding work volume. Now today we'll look at spatial descriptions. How do you define the position and orientation of the end effector with reference to the base coordinate frame and the various mathematical transformations that are involved. So today's class is about spatial descriptions and transformations. In the last class we looked at the various components that make up a robotic system. For example, the robot is made up of 4 parts. One are the joints. Okay, so these are the joints. Then we have links. So these are the links. And then we have the end effector, which is here, the end effector or gripper, and we have the controller, which is here. Okay, so these are the various parts of a robot. In the last class we looked at links, then we looked at joints. Today we'll be looking at how do you define the position and orientation of the end effector with respect to the base coordinate frame, and we said that this is the base and the base is fixed, it does not move. Now very quick recap. So there are different kinds of joints which are used. And they have different degrees of freedom. For example, the first kind of joint is a prismatic joint, which has 1 degree of freedom, and it's a translating kind of joint where the variable is a variable distance. So this joint can move like that, but it cannot rotate. The second kind of joint is a revolute joint, and the revolute joint can rotate about the axis, but it cannot translate, so it cannot move in that direction. Okay, and this also has degree of freedom 1. The other kind of joint is a cylindrical joint in which the joint can translate and it can also rotate. Okay, so this has 2 degrees of freedom and it's called a cylindrical joint. And we also define what is an axis. An axis is a straight line extending in both directions about which the joint is rotating in the case of a revolute joint. In the case of a translating joint, it is the straight line. For example, here it is the straight line about which the translation is taking place. That is called the axis. Now the other kind of joint is a spherical joint, which has 3 degrees of freedom. It is also called ball and socket joint because of the structure, that there is a ball which is inside a cup or a socket, and it can rotate. This one has 3 degrees of freedom, and it can rotate about the x-axis, it can rotate about the y-axis, and it can rotate about the z-axis. So it has 3 degrees of freedom. Now using this kinds of joints, the prismatic joint, the revolute joint, cylindrical joint, or spherical joint, we can make different kinds of robots. And we looked at the various different kinds of robots that can be made, and we also looked at the corresponding work volume of these robots. So this one is a Cartesian robot, and the work volume is a cube or a cuboid. Then this is an articulated robot, and the work volume of this robot is a sphere. So this is similar to our hand. Okay. Another robot we looked at is this Cara robot, which is used for electronic assembly, and the work volume of this robot is a hollow cylinder. Now we proceed further, and in today's class we'll look at how do we describe spatial descriptions and what are the transformations involved. So this is a robot, and the base of the robot is fixed. So we have a fixed based robot, and the robot moves in space. Okay, so these are the various joints, and these are and this is my end effector. Now the end effector or gripper is going to move in space. So for example, from here it comes here. Just for example, the end effector has come here. Okay, so this is the motion from here, it has come there. Now all the joints have moved, and the end effector has moved from one location to another location. Now we need to know what is the position and orientation of the end effector with respect to the base of the robot, right? So we have to define what is called, I need to know the position of a point. Let's say the end effector point is this point. Okay, I need to know the position of that point. And knowing the position is not enough. We need to know the orientation also, because the end effector could be in different orientations. For example, for a point here, the end effector could be like this, or it could be sideways, it could be like this. So the position or the position coordinate of the point is the same, but the orientation of the end effector is different. So we need to talk of positions and orientations. So let's proceed. Now what we need to do is, the first thing is that the base of the robot does not move. Okay, so it's fixed base, and this base we're going to assign a coordinate system. So all the measurements that we're going to make will be with reference to the base coordinate system, which we call the universal coordinate system, or the world coordinate, or the fixed coordinate. So this base is not going to move, and it's a fixed base. So please remember that this is a fixed base and it does not move. And the measurements we are going to make is with reference to this fixed base. Now we need to define the position of a point, the position of this point in space. Okay. So what we need to do is, let me draw a robotic system here. So this is a robot, and I have different links, and these links, there can be any number of links, and there is an end effector at the end. So what we are going to do is we are going to assign axis. Okay, let's call this a z-axis, z0, z1. Just for example, this is x0, this is y0. So for every joint, I'm going to assign an axis. Let's call this z2, this is x2, okay, this is z3, this is x3, like that, in that way. And I'll come up to here. So this is my, let's call this zn, this is xn. Just for example, n is the last joint. Now what I need to do is I need to find the position and orientation of this last axis or frame with reference to the base coordinate frame. Now you can see that what is the relation between them. This frame has moved from this 0 position to first position, then second, third, fourth, and then it has gone to the nth position. That means there are rotations involved, okay, and there are translations involved. So what are the two transformations? The transformations is a rotation transformation and a translation transformation that is going to take the last frame, the nth frame, with respect to the first frame. So let's look at it like this. We'll say that initially the two frames are the same. 0 frame and nth frame is the same. Then the nth frame is rotated and translated from joint to joint, and it goes to the end. So we need to define two things. We need to define the position of the origin of the nth frame. Okay, we need to define its position with respect to the end effector, so position, and then we need to define its orientation with reference to the base frame. So we need these two things, right? Now if I want to define the position of a point in space, how do you define the position of a point in space? So let's go to the next slide and look at position of a point in space. How do I define that? So this is a spatial description of the position of a point in space. Okay, so how do we do that? We have to define its position. How do you define the position? We define the position by first assigning an axis and then finding its projection on the corresponding axis. So we are using a few terms like frame. We have to define a frame, which is also called an axis. Okay, now we define a frame by assigning three axes. Let's call it the x, y. So this is my x, that's my y, and this is my z axis. Okay, now this is the point P, and this is my frame A. So what is a frame? A frame consists of three axes here, three orthogonal unit vectors. So what is an axis? Three orthogonal unit vectors. Okay, so so some things to note here very carefully. These are very elementary, but then we have to be very careful of this, is that it consists of three axes, they are orthogonal, and they are unit vectors. Okay, now why three axes? Or even before that, what is an axis? So an axis is a direction in space. Okay, that's the definition of axis. Now how many axes? Now here we are saying three axes. So why three? Three because we are dealing with 3D Euclidean space. So 3D Euclidean space has 3 dimensions. So we are saying 3-dimensional Euclidean space. That's why three axes, and they are orthogonal to each other. So this will mean a lot of things as we go along. So please pay attention to these small points. Now in robotics, we are defining a point P, and This point P is with reference to frame A. So in a robot, we can have multiple axes as just seen here. So when you're writing the position of a point, we have to be careful of also writing it is with reference to which frame. Okay. So I'm writing PA, which means point P with reference to axis A has coordinates x, y, and z. What is the meaning of this x, y, and z? It basically means this vector and its projection on the x-axis, y-axis, and z-axis. Okay, that is the meaning of Px, Py, Pz. Now, so the position of a point is defined by three position coordinates, and this is what we mean by position coordinates. Okay, so these are the three position coordinates by which you can define the position of a point in space with reference to an axis. So we always write the position with reference to an axis here. Now, is it enough to define the position of a point? No, because we have to define its orientation also. So for example, a body in space, I'm just giving an example, a rigid body like this has point P. Okay, now the body could have different orientations. It could be like this also. The point P has to be same. So it can be like this also, it can be like this also. So the point P is still the same in space, but the orientation of the body is different. So it is not enough to define the position only, we have to define the orientation also. So after position, what we need to do is we need to define the orientation of a point. So, sorry, not of a point. A point has only position, no orientation. So these are small things, but we need to be careful. So a point has position, but no orientation. So point has position, but no orientation. Okay. So we need to define the orientation of a body also. Now let's look at how do we define the orientation of a body. What we do is we fix a coordinate system. So this is my earlier coordinate system, x, y, and z. So x, y, and z system is here, and this is a body. Okay, so a body is like that, and we have a point P there. Now we fix an axis on this this body also, x, y, and z. Let's call it x, y, z. Okay, so this is my x, y, and z. Okay, now this is an axis A. Now this is an axis P. It's another axis. Okay. Now the position of the point P is with reference to axis A, so it is PA or AP. Now we have another frame which is called B, which is assigned to the body. Now how do I define orientation? So orientation is defined by taking the angles, okay, between frames B and A. Okay, so what is the angle made by the x-axis with respect of B with respect to frame A? Then what is the angle that the y-axis of B makes with respect to frame A, and the z-axis of B with respect to frame A? Now, position is defined by three coordinates, whereas the rotation of a body is represented by a matrix. Please note this, that the rotation is a matrix. Okay. What does this matrix contain? This matrix contains the x-axis of B with respect to A, x, y, z. This is y, A with respect to B, and this is z, A of respect to B. Okay, so this is the matrix, and if I write it in this form, so this will basically mean that R11, R12, R13, R21, R22, and R23. Then is R31, R32, and R33. Okay, what is this? Each of this corresponds to this one. So this column essentially is the angles made by the x-axis of B with respect to the x of A. Okay, this is with respect to the y of A, and this is with respect to the z of A. Similarly, the second one is the y-axis of B. What is the angle it makes with the x-axis, y-axis, z-axis of A? And this one is the z of B, what angles it makes with the x, y, z of A. Now these are columns, and we need to note that these are unit vectors basically. So the mod of each of these columns is equal to 1 because they are unit vectors. Okay. So something to note here, the position of a point is defined by three parameters, x, y, and z, whereas the rotation of a body is defined by a matrix, okay, which gives the relation between the frame on the body and with respect to the fixed frame or the base frame. Now, when we looked at this matrix, when we look at this robotic system, robotic manipulator, basically we see that there are frames and the origins of the frames are not the same and there can be angle between them. So if I were to explain it like this, that let us imagine how did this last frame go there. So let me imagine that the first frame and the last frame were initially the same. So this is my, let's call this the XY and Z system. Just to explain X, Y, and Z of A. Now I will say that initially they were at the same point. So the B also, I'll use a different color. So B is here. Okay, B frame X, Y, Z is red color. So this is X, Y, and Z. Now initially there was no angle between them. This is frame B. Okay. Then how did frame B end up going there? So first it rotated and then it translated. So it rotated with respect to A and then it translated from here to there, then from here to here, then from here to here, then from here to there. So from here it went here, then it went there, then it went there, then it went there. That means the origins moved. Okay, and there is a relative angle between them. So we see that there are basically two transformations. One is a position orientation. We have defined in terms of defining the spatial description of the body in space. Then there are two transformations, which is the rotation transformation and a translation transformation. Rotation between the axis and translation between the origins, okay, with respect to the base frame. So what we need to do is first we need to understand that if one frame rotates with reference to another frame, then how do you relate the coordinate of a system in a rotated frame with to that of the reference frame. Okay, so let's proceed and see geometrically. And the rotation matrix is a matrix. This also I've explained why it is a matrix. Okay, now let's start off by trying to derive geometrically that if we have a frame, this is one frame, this is my X, Y, and Z. Okay, so this is X, Y, and Z. So this color stands for the frame A. Okay, now initially we had another frame which is frame B, and this frame B had the same origin. Please note the origins are same, and this is my frame B. Okay, so this is frame B, X, Y, and Z. Now if I have a point here, BP, okay, if it has coordinates BP and AP, so the point is the same point you can see, okay, but its coordinates in two frames, if the frames have the same origin and they have no angle between them, then the coordinates will be same. This is X, Y, Z, that is U, V, W. So X, Y, Z is equal to U, V, W. Why? Because there is no rotation between them. Or what is the rotation matrix? It's an identity matrix, right? Now, if I say that frame B is rotated, okay, by an angle, so let's say my frame B is now rotated by an angle, let me draw it a little bigger. So this is my frame B, okay, this is X, B, this is YB of B, and Z remains the same, so it is rotated like this about the Z axis. Okay, so please note that the origins were the same, origins are the same. They were initially, they had no angle between them, the two frames. Then frame B is rotated by an angle theta, okay, in the counterclockwise direction, and where is my Y remains same here. Okay, so what has happened is now we have a point P here. Okay, what is this point P? This point is this point. Okay, now the point is point P, but because there is an angle between these two frames, the coordinates X, Y, Z will not be equal to U, V, W. That you understand from geometry. Now the question is, how do you find the relation between X, Y, Z and U, V, W? Okay, that's what we are trying to do. Now if you can find that matrix which relates PB with PA, then I have a transformation, so which is called the rotation transformation. So how do we define it from geometry? Now X, Y, Z, what is the meaning of X, Y, Z? So please watch this carefully. What is the meaning of X, Y, Z? It is the projection on the X-axis, projection on the Y-axis, and the projection on the Z-axis. So this is my X, that's my Y. I've written in blue color. Okay. Now what is UVW? UVW is the projection on frame B. Sorry, I have written it the reverse. Sorry. I have reversed the writing. So please be careful. UVW is here, and this is X, Y, Z. Okay, please note that. Now, what is UVW? UVW is the projection here. So that's my U, and that's my V. Okay, that's my V. And what is W? W is projection on Z. Okay. Now, what is the relation between these two? If I take a simple construction here, okay, this is a very small construction I'm making. So this is the construction, and this is also my angle theta. Okay. Now, if we were to see what is the relation between these two, geometrically, let's see. So x is equal to what is x? X is this length, which is this one. So x is equal to this total length, which is equal to u cos theta, okay, minus this small length, which is equal to v sin theta. Construction I've made is that this is I'm making this triangular construction. This is my angle theta. So you can see from here that this full length from here to here is equal to u cos theta minus this small length. So this length is equal to this length, which is equal to v sin theta. So this is my v. Okay, this is v. So it is x is equal to u cos theta minus v sin theta. Okay. Now what about y? What is y? Y is this total length from here to here. Okay. Now what is y equal to? Y is equal to this much. Okay, plus this much. Okay. So how much is that? The top one, this much is equal to this much. Okay, which is equal to v, which is equal to, sorry, just this one plus this one. So this is equal to u cos u sin theta plus this much, which is equal to v cos theta. Okay. So we are seeing the relationship between the xyz coordinate system in reference frame A with respect to the coordinate system expressed in reference frame B. Okay. So x is equal to u cos theta minus v sin theta, and y is equal to u sin theta plus v cos theta. And what about z? Z is equal to w. Why? Because there is no change in the z direction. Okay. So if I write it in matrix form, then x, y, z is equal to u cos theta minus v sin theta, and this is equal to, sorry, let me write it in matrix form, and I will write it like this: cos theta minus sin theta, and this is sin theta, this is cos theta, this is 0, 0, 1, this is 0, 0, and on this side you have u, v, w. Okay, so this is in matrix form. Now this matrix is called the rotation matrix. Okay. Now what is the rotation matrix? The rotation matrix is a 3 by 3 matrix. Okay, so first of all, it's a 3 by 3 matrix that relates the coordinates of a point in relates the coordinates in a rotated system, in a rotated frame, to the reference frame. Okay. So that is the definition of a rotation matrix. Now this is very, very important, but it's very, very simple. Okay. So I will go through this again. I will go over this again. Okay. So I will just describe what I did, and you should be able to do it by yourself. If you understand it once, there is nothing to memorize. There is nothing to by heart here. So we have two frames. We have one frame. Let me draw it a little bigger. Okay. So this is my x-axis. That's my y-axis, and this is my z-axis. Okay. So we have two frames, frame A and frame B. This is my frame A. Okay. And we have another frame which is rotated, which is the red one, which is here. So this is my x, this is my y, and this is my z. Now frame B. Frame B is red color. Now if you have a point here, which is point P, it will have coordinate in frame A as well as in frame B. Okay, so this is x, y, z, and this one is equal to u, v, w. Okay. Now what is the meaning of this? This means this is the projection on the x-axis. This is x, that is y. So this is my x and that's my y. Now in terms of A. In terms of B, what does it mean? This is my projection on the b-axis. Okay, so this is my u, and on the y-axis the projection is here. So this is my v. right? And this is my angle theta. Now I'm trying to find the relation between x and y. So what is x equal to? X is equal to, if I take the projection, I make a construction. The construction is this one. Okay, this is my angle theta. So if I make that construction, then what we see is that this distance is equal to x. Okay, so x is equal to this distance. X is equal to this total distance, which is equal to u cos theta, minus this small distance, which is equal to, so this distance is equal to this distance, which is equal to, this is v, which is equal to, this is also v, so it is equal to v sine theta. Okay, so this is equal to v sine theta. And y is equal to, what is y? Y is this full distance. This full distance is equal to this distance plus this distance. So this distance here is equal to u sine theta plus this distance is equal to, what is this? This is equal to this, which is equal to v cos theta, and z is equal to w. So what we see is that it's very easy to obtain this relationship. There's nothing to by heart. Once you make this geometrical construction, you know what the matrix is. And the interesting part is that for x and y, only those cos sine, they change positions. Okay, so what we have got is, we have got the rotation matrix. We write it as r a z by an angle theta. Okay, so a to b, rotation is about the z axis by an angle theta, and this is given by cos, I'm writing in short, so cos minus sine, sine cos. Okay, we can say cos theta, sine theta, cos theta, 0, 0, 1. Now something to note here is that each of these columns are unit vectors. So this is my x, that's my y, and that's my z, as I just showed a couple of slides back. So x mod of x is equal to mod of y is equal to mod of z is equal to 1. And the dot products x dot y is equal to x dot z is equal to y dot z is equal to 0. Okay. Now the other important parameter is that because these are column vectors, the determinant of this matrix, determinant of r z theta, is equal to 1. Okay. Now you can also note that the rotation is about the z axis, so this element here is become 1, and this is 0, 0, 1. On this side also it is 0, 0, 1. Why? Because the rotation is about the z axis. So these are things which you should note and understand geometrically rather than just by looking at a matrix. Now this is called a proper orthonormal matrix. And the property of this proper orthonormal matrix is that R inverse is equal to R transpose. Okay, this is an interesting property which we're going to make use of. So whenever we talk about finding the inverse of the rotation matrix, we simply take its transpose. We don't do adjoint of R by determinant of R. We don't do that. Okay, so let's proceed now. And so these are some of the properties. So how many properties are there? There are 6 properties. Okay, so there is the mods are equal to 1 and the dot product is equal to 0, gives us 6 properties. So this basically means that your rotation matrix R A to B, Z theta, it is 3 by 3, which means it is 9 elements. Okay, but you do not need 9 elements to represent the rotation of a body in space. Okay, this is interesting. Why? Because you have 6 constraints, which means that those 9 elements are not all independent of each other. Okay, there is some relation between them. And what else? What is the relation? The relation is this 6 equations here, that the mod is equal to 3, mod of each of the columns is equal to 3, and the dot product is equal to 0. Okay, so if we take that into picture, then the number of independent parameters you need is 9 minus 6 is equal to 3 parameters are required to define the rotation of a body in space. Define the rotation matrix. Okay, so this is an interesting thing to note and something to keep in mind. Now let's look at a very small problem which will make it very clear. So we have this very small example that a frame B is rotated by 60 degrees about z-axis of A. Okay, so if BP, the coordinate of the point P in frame B, is given by let's say 1 1 1, just for example, find AP. Okay, I hope the question is very clear. So we have two frames. We have one frame which is my A frame. Okay, this is my A frame. This is X, Y, and Z, and the frame B has been rotated by 60 degrees about. So the frame B here has been rotated by 60 degrees. Let me change the color. So the frame B is rotated like this, and it's here. So this is my frame B. This is rotated by theta, and the point is P. So BP is equal to 1 1 1. I want to find what is AP. Okay, this is the question. Okay, so this is my vector here. Okay, so this is the question. How do we find AP is equal to the rotation matrix cos theta. Theta is equal to 60 degrees here now. So let me write AP is equal to cos 60 minus sin 60, sin 60, cos 60. This is 0 0 1, that is 0 0, and coordinate of BP is equal to 1 1 1. Okay, so writing AP is equal to R Z theta, this matrix, into BP. That's where we have got it from. Okay, so all you need to do is just put the number values and then multiply, and you get the answer. Okay, so we'll be getting what is AP. So this gives a clear idea of your rotation matrix. Okay, now let's look at another property, not a property, but we are seeing that there are you can rotate about the z-axis, you can rotate about the y-axis, you can rotate also about the x-axis. Okay, so what we just looked at here is rotation about the z-axis. Now similarly, I can rotate about x, I can rotate about y also, right? So if you are rotating about x and y, what would happen is, let me just very quickly explain it. So this is my frame A, this is my x-axis, y-axis, and z-axis now of A. We have another frame which is rotated now by means of let's say by an angle theta. Okay, and let me call it some other angle. Now let me call it alpha. So this is my rotated frame B now. Okay, so x, y, and z is rotated now. Okay, this is my x-axis, but the rotation was with reference to the x-axis now. Now if I use the same logic, you can actually derive it geometrically. I'll leave that as a homework for you. Okay, that if you do it exactly the same way, you make the projections on the x-axis, the y-axis, and then geometrically find out what is the relation between u, v, w and x, y, z. Okay, you can very easily do that geometrically, and what we'll get is the matrix, rotation matrix about the x-axis by an angle alpha is equal to, if you can guess, it is a rotation about x-axis, so the coordinate on x cannot change. Okay, so this is cos theta, so minus sin theta, this is sin theta, this is cos theta. Okay, now this is for rotation about x. Now as a homework, you can find out rotation about y. Okay, exactly the same way. Okay, now now let us, so this is your homework. Make the geometrical construction, make two axes, rotate, and geometrically derive. Okay, it's very, very easy. Now the interesting thing here is that we are rotating about the x, y, or z axis, right? But if you rotate twice, for example, I rotate about the x, z axis, then I rotate about the x axis, okay, then what will be the compound rotation matrix? That's one question. The second question is, suppose I rotate about the fixed frame once, okay, but the second time I rotate about the rotated frame, then what happens? Okay, so let's look at this now, that I'm going to rotate about the fixed axis. So there are two or three ways. One is called the fixed axis rotation, and the second is called the Euler angles. In the fixed axis rotation, we rotate always about the fixed axis x, y, or z. Okay, and in the rotated system, we can rotate about the rotated axis. Okay, now they are going to be different. Why? Very simply, you can understand that these are matrices, so matrix multiplication does not commute. So if you rotate about a rotated system and you rotate about a fixed system, it should not be same. Okay, and also A into B should not become equal to B into A. Why? Because these are matrices. So let's look mathematically what it means. Now, if I just go back a little bit here, okay. So in this problem, so let's call this exercise 1. Now let's call it exercise. Let's have another one, exercise 2. Okay. Now it's exactly the same as question number 1, but I want to find. I'm given AP. AP is, for example, 2, 2, 2. I'm given AP. I'm asked to find BP. Okay, can you do this problem, or can you think how it will be done? So in this system, I have given you AP, BP, and I asked you to find AP. Now, can you find BP if AP is given now? Okay, so this is the equation remains the same. AP is equal to RZ theta into BP. What will BP be equal to? BP is equal to RZ theta inverse into AP, right? And you know what is this inverse? So RZ theta inverse is equal to RZ theta transpose. So that's very easy. So you have the same rotation matrix, you just take its transpose, you get the inverse of that, right? So once you geometrically derive it, and I would insist that you please derive it like this. Okay, so please draw the matrix, draw the axis, derive the rotation matrix geometrically, and you'll never forget it again. There's nothing to by heart here. Okay, and most of the rotations are about z, so if you just know that z axis, it's enough, the rotation about z. Now let's look at the two ways by which we determine axis, or determine or we define rotations. This is called the fixed angle rotation. Okay, in the fixed angle rotation, we call it the x, y, and z fixed angle rotation. That means we are rotating the frames always with reference to the fixed axis. Let's draw and see what happens. So this is my x-axis. Let me draw it a little bigger. So this is my x-axis. Let's say z-axis x, or whatever. Let's call it x, y, and z. Okay, so this is my frame A. We have frame B. Frame B, which is initially the same frame. There is no rotation between them. So frame B is also here, but it's red color. X, y, and z. Okay, so this is my x, this is my y, that is z, this is x, but red color. Initially, they are the same frame. So what is the rotation matrix? The entity matrix, right? Now, I rotate B about x axis by an angle alpha. Okay, so my first rotation is rotation of alpha about x. This is my first rotation. Okay, this is number 1. Now, if I do that, what will happen is, you can imagine what will happen is, because the rotation is about x-axis, the x-axis will not change, but the y-axis will change position. It will come here. So let's call this y dashed. Okay, the z-axis has gone there, so it becomes z dashed. The x remains the same. Okay, this is what has happened. This is my angle alpha. Next, what I do is, I'm going to rotate it about the fixed frame. We could have also rotated about the rotated frame. That means the next rotation is about the y-axis. So it could be the fixed y or the rotated y. Okay, so in the fixed frame, it's always about the fixed axis. So I'm going to rotate about the fixed axis. Let me change the color, and I'm going to rotate like this now. Okay, now what is going to happen is, the y dash will remain same. Sorry, I'm going to rotate about the fixed axis. The fixed axis is here, right? So what is going to happen is, if you can imagine, y dash will go here, y double dashed, z double dashed, and your x, that's called double dash, this is double dash, just come there. Okay, so my second rotation was rotation of let's call it angle beta about y. So this is my angle beta. Okay, so I have rotated my angle, I have rotated frame B by an angle beta about the y-axis. Okay, it has changed direction. Now let me rotate about the z-axis. Now we are always rotating about fixed, so this is about fixed frame rotation. Now what would happen is your x-axis has come here. Okay, your y-axis has gone there, and your z-axis remains the same. No, sorry, z of this rotated fellow has rotated. Okay, it has gone there. So now this shows us that this is my rotation, third rotation, r alpha gamma, let's call it alpha. So gamma beta alpha, let's call this alpha. Okay, now this is giving us 3 rotations, and the order in which we rotated was like this. Okay, but now when we are finding the combined rotation matrix, I'm going to multiply in the reverse order, so it will become r alpha z into r beta y into r gamma x. Okay, this is my combined rotation matrix. This is my combined matrix, and the order has reversed. Order of multiplication is reversed. Okay, that you can note, right? So we first rotated by gamma, then beta, then alpha. But when I'm multiplying it, it's becoming alpha, beta, gamma. I'm reversing the matrix multiplication. Now we are doing that because matrices do not commute. We know A cross B is not equal to B cross A. Okay. And when we are multiplying, when we are rotating about the fixed angle rotation, the rotation matrices pre-multiply. Okay, so let's look at a very simple example. So very simple example here. A is a matrix B. So a matrix B, or rather a frame B. Okay, a frame B is rotated by let's say 30 degrees about z of A. Then it is rotated, it is again rotated by 60 degrees about x axis of A. These are fixed frames. Now if you are given BP is equal to a particular coordinate, let's say 1, 1, 1. Okay, find what is AP. Okay, now there are 2 rotations. Please note that the first rotation, if I draw it here, let me draw. So the first rotation is about the z-axis. So this is my z-axis of A, this is my A, x, y, and z. Okay, so the first rotation has brought about the z-axis by an angle 30 degrees. Okay, so this was my first rotation. So your y has gone here. This is my x, and this is my y. Right? So this is my first rotation. What about the second rotation? It is then rotated by 60 degrees about the x-axis. So this is my second rotation, and with the second rotation, what is happening is, so my second rotation is like this, 60 degrees. So now what is happening is your z-axis is coming here, your y-axis is going there, and your x-axis is coming there, x of B. Okay, so this is B frame. Okay, now it has gone there. Now we are given this point PB. We are given the coordinates as 1, 1, 1. We are asked to find what is its coordinates in frame A. How do we find that? We basically have a combined rotation matrix now. And please note that in this combined rotation matrix, we pre-multiply. So it was, rotation order was RZ 30, then number 2, it was RX 60, right? So when we are going to multiply, we are going to pre-multiply, it will become RX 60 into RZ 30. Okay, please note that. And that is going to be my combined rotation Z30 and X60. Okay, so this is a matrix. Okay, so this is a matrix, right? What will be this matrix looking like? So this matrix is going to become cos 60. Let me write it in short. I'm writing C for cos. So cos, so it is going to become x. So it is going to become 1 0 0 0 0. So this is cos 60 minus sine 60. So this is sine 60 and this is cos 60. This is the rotation about x-axis. The next one is the rotation about z-axis by 30. So it is cos 30 minus sine 30. So this is sine 30, this is cos 30, 0 0 1 0 0, right? So now when I can simply multiply these two matrices and I get my combined rotation matrix. Okay, so what will be the answer to the problem? The answer to the problem is going to become AP is equal to the combined rotation matrix of R. What was the order? The order was X, and then the order was Z in that order, and into BP, which is equal to whatever is the matrix that you get. Okay, these two matrices. So I can write it again. So what was the rotation? RZ, it was 60 and 30, right? X was 60 and 30. So X was 60, so it is 1 0 0 0 0. So cos 60 minus sine 60. This is sine 60, this is cos 60. Okay, multiplied by Z, which is equal to cos 30 minus sine 30. This is sine 30 cos 30, 0 0 1 0 0. Okay, and here it is. PP was given as 1 1 1. So this is my AP. Okay. Now on similar lines, if I were to give the same question, but I'm giving you AP as 2 2 2, find BP. How do you do that? Okay. Now it's very, very simple, because this combined rotation matrix is also a rotation matrix. So the columns are still orthogonal. It is still an orthonormal matrix. So all you need to do is take its inverse, and the inverse of that is the transpose. So there's no problem there, right? So AP is equal to R X rotation and R Z rotation into BP. And if I take BP is equal to the inverse of this. So R X rotation and R Z rotation inverse into AP. So this is AP, right? And this one is equal to Rx, Rz transpose, because it's a proper orthonormal matrix again. So you can go from one side to the other side very easily simply by taking the transpose. Okay. Now if you're multiplying with more than one matrix, okay, you just keep pre-multiplying. Okay. So I gave this example here where we have three rotations. We have by alpha, we had by gamma, then by beta, then by alpha, right? So when we are making the combined rotation matrix, we are simply pre-multiplying. Now this is important, and it's very simple to remember. You should remember something which is called shoes and socks. Shoes and socks. Okay, so you first put on your socks. Okay, then you put on your shoes. Okay, but when you're removing it, what would happen? You first remove your shoes, and then you remove your socks. So if you notice that the order has reversed. Okay, so when you remember about matrix multiplication for rotation matrices, you should just remember shoes and socks, and then it reverses the process. And you can remember that even for matrices the same thing happens. Okay, now we can of course have another kind of rotation matrix, which is called we can have another system of rotation in which we are rotating about the rotated system. Now this is called the Z, Y and X. Okay, now I just forgot something. I'll just this X, Y and Z, X, Y and Z fixed angle rotation is also called the roll pitch yaw. So roll pitch yaw system of rotations. When we say roll pitch yaw at the wrist, this is what we mean, XYZ angle rotations. Now we can have another type of rotation which is called the Z, Y and X style of rotation, and this is called the Euler angles. Okay, these are called the Euler angles of rotation. Now in the Euler angles, we are rotating about the rotated system, rotated frames. Okay, now let's look what this would be like. Before we look at what happens, we define our XYZ, the reference frame A. So this is my reference frame X, Y and Z. So this is my X, Y and Z. So the first rotation I'm going to do is about the Z axis. So Z angle rotation of B is alpha. Okay, so there are two frames. Okay, this is my frame A and let's say this is my frame B. Let's call it rotation is about Z. So let's put this as Z. It's easier to visualize. Z, X and that is Y. Okay, so there are two frames, frame A, frame B. They're initially the same. Frame A is black and frame B is red. Okay, so frame A is this one. This is my X. Okay, so the first rotation that I'm going to do is about the Z axis, so I'm rotating. And in the first case, you see that there is no difference. The rotations will be the same, and what will happen is B will go there. So this is by an angle alpha, so B has gone there. So this has become my X, this has become my Y. Okay. Now in the second rotation, what we are going to do is we are going to rotate about the, this is first rotation. The second rotation, what we are going to do, we are going to rotate about the Y axis. So it is Z, Y. So rotation about Y of B by an angle beta. Okay. So now we are going to rotate about Y axis. So this is Y axis. Y axis is here now. Okay. So if I rotate about the Y axis, what you can see is it is rotating about the Y. So what will happen is the X will change and the Z will change. Okay, and Y remains here. Okay, so what has happened is the Y axis has changed. The X axis and the Z axis has changed now. Now in the third case, what we do is we rotate about. Let's put another color. The third case, we rotate about X axis by an angle alpha. So alpha, beta, let's call it gamma. So rotation of B by an angle gamma. So I'm rotating about X axis now of the rotated one. Okay. Now what is going to happen is your Z will change and your X will change again. So X, Z. This is only a representative figure. Depending on the angle and the direction, it will change. But there will be a change on the Z axis and the Y axis. So your Y and Z has gone this side now. Okay, so this is your Z and that's your Y now. Right. So what we did is we rotated about the Z axis, then we rotated about the Y axis, then we rotated about the X axis, but of the rotated frames. Okay, please note that. Now we have three rotation matrices. This is going to be rotation matrix Z alpha. This is going to be rotation matrix. This is going to be rotation matrix R, Y, beta, and this is going to be a rotation matrix R, X, gamma. Okay, but here what we note is that the combined rotation matrix, okay, will be the product of the matrices in the same order: Z alpha, R, Y, beta, and R, X, gamma. Okay. So whatever was the order of rotation, first, second, third, that order does not change and it remains the same. So this into this into this. So please note that Euler angle rotations will cause change in your the way we are rotating the because we are rotating about the rotated system, rotated frame rather. What will happen is the matrices will not change. We will not pre-multiply the matrices. The order will remain the same. Okay. Now this is something to remember, but in robotics we will normally go ahead with the fixed angle rotation only, because it gets a little confusing, as you can imagine, that if you start rotating about the rotated axis, then your base itself is rotating with reference to that axis now. Okay, so the concept of putting a fixed base doesn't help. So it gets very confusing. So in robotics, what we'll be doing are transformations. So in robotics, basically, when we are putting our frames and rotating, we will be using the fixed angle kind of rotation. Okay, fixed angle rotations, which will mean that you need to pre-multiply. Okay, please note that. Now, so we can do a very small problem here. Let's look at this problem, the same kind of problem with a little twist. So frame B is rotated by 60 degrees about Z of A. That's the first rotation. Then it is rotated by 30 degrees about X of B. Now please note carefully, this is rotation about then it is rotated by 30 degrees about X axis of B. So now if you're given BP is equal to 1, 1, 1, okay, what is AP? Okay, how do you find that? So AP is equal to, this is a rotated system, please be careful here. So it is going to be a rotation about Z60, okay, into rotation of X30, okay, and this is going to be my BP. Okay, so what we can do is we can simply write the matrices and get the number. So this is going to become cos 60, that is cos 60 sin 60, then sorry, minus sin 60, sin 60 cos 60, 0, 0, 1, 0, 0. Then this is your cos, so this is a rotation about X, so it is 1, 0, 0, that is 0, 0 there. So it is cos 30 minus sin 30. It is sin 30 cos 30. And this is my BP is equal to 1, 1, 1. Right? So this is my AP. Okay. So what we noted here is that we have not pre-multiplied the matrices. We keep the order of multiplication the same. The order of rotation, the order of multiplication is the same. But in robotics, we normally don't do this. Okay, but just note that this is also there. Now, what we have seen is we have talked about the rotation matrices, and we can have any number of rotations. If you're rotating about the fixed axis, then you just pre-multiply the matrices. So it's as simple as that. Now, we can look at, so we have finished our rotation matrices. Okay, and we have three rotation matrices. We can be our rotation about Z by an angle theta. We can have rotation about X by an angle, let's say alpha, and we can have rotation about Z by an angle beta. Okay, and whether it's a fixed angle rotation or a rotated angle rotations that we are following, you either pre-multiply or you don't pre-multiply. Now the next thing that we need to know is that we need to look at translations also. That means the frame from here, this is my Z0, Z1, this is X0, X1, Z2, X2, in that order till the last it has got to Zn, and this is my Xn. Okay, so what we notice here is that the origins from 0 frame has moved to the last frame or nth frame. That means it has translated and gone there. So there is a rotation and there is also a translation. So we also need to look at a translation transformation that will take care of when the origin moves, what happens. So we will stop here today, and in the next class we are going to talk about the translation operation. Okay, what happens when you translate and rotate two frames, and that will give us a homogeneous transformation matrix. Something to remember here is that this is a 3 by 3 matrix because we are essentially in 3D Euclidean space. Okay, that is why it was 3D, and the various properties of the matrices that are involved. So we'll stop here today. Thank you.